Let's jump right into this explainer and talk about how to stop your .NET shared libraries from turning into an absolute, unmanageable dumping ground. If you've been writing .NET code for any length of time, you already know the exact dread I'm talking about. You open up a solution, and sitting right there, staring back at you, is a monster project named common.utils, just waiting to ruin your day. Well, today, we are going to fix that. We're looking at a frankly brilliant modular monolith approach that uses dependency inversion and project references to keep your codebase clean, strictly bounded, and completely sane.
Here is our architectural blueprint for today. We'll define the black hole problem, look at slicing by business feature, apply dependency inversion as our guardrails, wire up the monolith, and then compare all this to some other common architectures. Let's get right to it.
Section 1, the black hole problem. We're starting with something every developer knows intimately, that one shared project where code just goes to die.
You know how it goes, right? It always starts innocently enough. You have a single helper class, maybe a simple string formatter. You write a really neat piece of logic, you realize another feature needs it, and boom, you pull it into a shared library. Totally reasonable. But eventually, you wind up with a massive project named core, shared, or utils. It grows so quietly, just one innocent static class at a time, while your team is busy shipping features.
Over time, this abused shared kernel actually grows its own gravity. Every new class just drifts into it because, let's face it, dropping something into a common folder is the path of least resistance. But here's the core issue. Because it's shared, everyone owns it. And when everybody owns it, nobody actually owns it. Suddenly, you can no longer reason about a change in isolation because every tiny change ripples everywhere.
And wow, things really just compound from there. You hit absolute dependency hell. A single circular reference pops up and forces these completely arbitrary splits into common.core or shared.models, turning your beautiful solution into spaghetti. Then, you hit a convention vacuum. Does a fresh data transfer object belong in models or contracts? People just start guessing, and the mess deepens.
Ultimately, the entire rationale for past decisions gets completely lost. When you have to rely on a git blame from a refactor way back in 2019 just to understand why a basic string extension is sitting in utils instead of core, you have a serious problem on your hands. As the source material perfectly puts it, this is archaeology, not architecture.
Moving to Section 2, slicing by business feature, it's time to pivot and change the very axis of how we split our code.
So, a huge part of how we get into this mess to begin with is our habit of splitting code by technical layers. Think about it. When you smear a single create user feature across 4 completely different technical buckets like data, models, and services, those buckets inevitably become unmanageable catch-alls. The fix here is to slice by business feature instead. Give one folder per feature, like user, currency, or dashboard. Everything that specific feature needs lives right there together.
Now for Section 3, dependency inversion as guardrails. This is where we introduce our absolute magic weapon to physically fix the spaghetti code.
Instead of dependency inversion just being, that standard answer you recite in a job interview, we're going to actually use it to dictate our physical module structure. High-level and low-level modules must depend on abstractions. In our context, this simply means features must only ever depend on each other's contracts, never, ever on their internal implementations.
Here is the actual blueprint for a compiler-enforced modular monolith. Just look at how clean this setup is. Every single feature is split into 2 distinct projects. The contracts project contains only interfaces and DTOs, and crucially, it references absolutely nothing. Then, the implementation project contains the concrete logic. It can only reference its own contracts and the contracts of other features. Finally, the host sits right at the top to wire everything up.
This right here, this is the punchline of the whole approach. Because an implementation project has absolutely no reference to another feature's internal logic, the compiler simply says no if you try to cross the boundary. You literally can't accidentally instantiate a private service because your project doesn't even know it exists. It's a hard, physical boundary. It is not some gentle guideline you have to constantly police during code reviews.
On to Section 4, wiring the modular monolith. This sounds amazing in theory, but how do we actually plug these heavily restricted features into a running application?
It comes together through a really specific, elegant lifecycle. First, you make those contracts your public API. But crucially, and don't miss this, you mark your concrete implementation logic as internal sealed. It becomes totally invisible outside its own assembly. To let the app actually run, each feature provides exactly one public hook, a registration extensions class.
The host's program.cs then calls this hook to blindly orchestrate everything, injecting dependencies at runtime without ever seeing the concrete types.
Now, a quieter, but honestly incredible benefit here is that the physical folder literally becomes the feature. Because everything is grouped perfectly together, that folder becomes the undeniable home for domain readmes, test suites, and most importantly, a code owner's file. It gives ownership a physical address, which completely solves that nobody owns it problem we were talking about earlier.
Finally, Section 5, Comparing Architectural Alternatives. Let's see how this stacks up against the architectures you probably already know. So, while the black hole approach scales terribly, and standard vertical slices can sometimes suffer from boundary drift if your team isn't perfectly disciplined, our compiler-enforced approach actively guarantees boundaries. It gives you a clear owner per feature. Is there a trade-off? Yeah, for sure. It requires more project files, and you have to do a bit more wiring up in the host. But honestly, for the sanity it provides your team, it's a wildly worthwhile trade.
And actually, here's a super common misconception. You don't have to pick just one of these architectures. These concepts compose, they do not compete. Think of a feature like a heavy-duty safe. The contracts project is the boundary at the edge. But if the implementation inside that safe starts getting too complex, you can literally run clean architecture right inside that specific implementation project. The boundary outside does not care at all what you do behind it.
Okay, let's wrap up with some core takeaways. First and foremost, stop feeding the black hole. Shift your mindset and start slicing your solution by business feature, not by arbitrary technical layers. Share only the contracts, keep your implementation strictly private, and let your CS project files do the heavy lifting of boundary enforcement. Free your team from relying purely on discipline.
I want to leave you with this thought. Tomorrow morning, take a hard look at your solution. Look at that core or utils folder. Are you going to keep wrestling with that black hole every single day? Or is it finally time to let the compiler be the bad guy for a change? Thanks so much for joining me on this explainer, and happy coding.